Hello, everyone, and welcome back to the Cisco Optics Podcast, where we talk about pluggable optics for networks. Lasers have been around for over 6 decades. Since their invention, they have found their way into many applications that have changed our lives. Optical communications is, of course, one of them, and there are many that may surprise you. There's also still plenty of room to take laser performance to new heights, leading to even more new applications. This is episode 43, and we conclude our conversation with laser and optics expert Juliet Gopinath, professor at the University of Colorado Boulder. We wrap it up with a project using Raman spectroscopy to help prevent membrane fouling for freshwater generation. She also describes the motivation behind her Coursera course on active optical devices. Juliet Gopinath is the Alfred T. and Betty E. Look Professor of Electrical, Computer, and Energy Engineering and Physics at the University of Colorado Boulder. She received her BS degree in electrical engineering from the University of Minnesota and her MS and PhD degrees at MIT. She was a member of the technical staff at MIT Lincoln Laboratory from 2005 to 2009. Since then, she has led a research group at the University of Colorado Boulder. Her current research interests include ultrafast lasers, nonlinear optics, mid-infrared materials, spectroscopy, orbital angular momentum, and adaptive optical devices. She has published 78 peer-reviewed journal articles and over 97 conference presentations. She is a recipient of an R&D 100 award in 2012 and is an Optica Fellow. She served as an associate editor for the IEEE Photonics Society Journal from 2011 to 2017, the associate director for Qubit in 2019, and is currently an associate editor for Optica. Juliet also teaches a free online course on active optical devices. Just go to Coursera.org and search on active optical devices or search on Juliet Gopinath. If you haven't already, please subscribe to this podcast. On Apple Podcast, you would click the follow button at the top now. We're part of the Cisco Podcast Network. Check out our blog at blogs.cisco.com and search on hashtag Cisco Optics Blog. All one word, no hyphen, and no spaces. You'll find podcast notes and links there too. For our YouTube playlist, go to youtube.com and search on Cisco Optics. And for product information, go to cisco.com/go/optics. And now join me as I talk with Juliet Gopinath.
We have also been looking at membrane fouling. So when you think about generating fresh water from seawater, often you will use a reverse osmosis membrane to generate the fresh water. And over time, these things develop films and they have to be replaced. And so, it's obviously annoying to have to replace them. And as they're developing the films, it essentially means that you get less fresh water coming out. So there's
a film because it's like the gunk is just building up. Is that what the film is made of?
That would be the non-technical way to say it.
Yeah.
Yes.
Well, that's the only way I know how. So.
Yes. Well, so we have been specifically looking at what is called scaling, which is the deposit of crystalline material on these membranes. And essentially, this is a pretty common phenomena. And you can, for example, monitor how much fresh water is coming out. But by the time that decreases, that fresh water is called permeate. By the time that decreases, it's a little on the late side. So you really like to be able to understand the early onset of scaling and the dynamics, and then understand what remediation measures can be taken. And so for us, we've been using Raman spectroscopy. And so Raman spectroscopy essentially is that if you shine a color of light at a material, then if the material is what's called Raman active, it can excite lattice vibrations, and those will inelastically scatter the light so that it will change the color of the light that comes back. And if you detect the color of the light that comes back and you look as a function of wavelength, you can essentially get a chemical fingerprint of your molecule. And so this is a really powerful technique. And so what we've showed is that we can actually use this for real-time detection of scaling. of both calcium carbonate and calcium sulfate. And on top of it, we also showed that we could clean and get rid of some of the deleterious effects. And so we're really excited about this because we think
clean meaning remove the film.
Yes. So if you switch the feed to DI water, like if you catch it early enough, and then you switch your feed from whatever had the salts or whatever, if you switch that to clean water, then you can essentially reverse most of the effects. And so water is going to be a huge issue for the next generation. It's already becoming an issue for our generation. And so I'm actually really excited about this because here you combine this, maybe like somewhat complicated spectroscopy technique with this real world need, and showed something that I think has really a potential to be quite practical.
Yeah. Sorry. Tell me more about the way that you clean. You're actually breaking up the material, or how does, because the first thing you described was the Raman spectroscopy, so you're just sensing what the chemical is, right?
Yes.
But then in the same step, are you affecting the chemical by removing it? Or is that a different process?
So when we did our experiments, we actually have a high pressure flow cell, and then we have a feed solution that comes in. And so often we put the calcium sulfate or the calcium carbonate in the feed solution so that we can monitor the thing as it deposits. We can also take scanning electron micrographs to make sure that the Raman is telling us the right thing if we stop it. So the point is there's an optical window that we use to interrogate this. And if we detect a Raman signal from one of these components, we can switch our feed stream to just DI water, and then essentially you wash everything off the membrane, and then you can switch it back.
Okay.
So in real plants, they use what are called spiral wound membranes. Our work was done on a flat sheet membrane, but it's quite possible in one of these plants to have a bypass stream where you have a flat sheet membrane that you can do this monitoring.
Okay. So you're not affecting it optically. It's really the DI water.
That's right.
Okay. But does the DI water remove it as a result of something you did optically, or is that just a thing on its own?
The optical spectroscopy is honestly just an interrogation. It's a monitoring system. We do not do anything like, turning up the power to the point where we could, where we could disassociate the material or whatnot.
Okay.
We're not doing anything that exciting.
All right.
No LIBS, no laser induced breakdown spectroscopy.
Okay. All right. Wow. So this is a really nice palette of both, like you started with very, very fundamental physics to this very, like you said, a very real world problem that, literally affects our lives and our health today, right? And everything in between. Is there anything else, any other research topics you want to bring up?
That's about all I can think about right now. I think it's a little bit too much.
It's plenty. Yeah, for sure. All right. And I also know that you developed a course that's available to pretty much anybody, right? Do you want to talk a bit about that?
Yes. So I am a 5th generation engineer, and my dad is from India. And so I think as I've become older, I've been really appreciative of the opportunities that I've been provided. I mean, a lot of what you get is because, you worked for it, but I think there is a significant element of luck, in the sense of, where were you born? Where did you grow up? That's going to determine to some degree what happens with the opportunities. And so
what time period were you born, right?
Exactly. I mean, if you were born 200-300 years ago, your life expectancy was really small compared with now. So I really wanted to do something to give back and to provide opportunities to people, especially women, and especially maybe in countries where it may be harder to get opportunities. And so I've been teaching a course on active optical devices. That's essentially, we learn about LEDs, we learn about lasers, we learn about how do you detect the light, and we also learn about displays. So it's a pretty advanced course. And so if you don't happen to be at the University of Colorado, you can't really take my course. But now you can. I've developed what's referred to as a MOOC. It's a massive online course. And so essentially, I have recorded a series of lectures, and I've placed this course as a specialization on Coursera in three modules or courses. And so now anybody can look at this material for free. If you want to be able to do the homework, I believe there is a small fee. And this course is also part of the University of Colorado Electrical, Computer, and Energy Engineering online master's degree. So if you want to get a master's degree this way, you can also take my course for credit. But I guess I feel really proud that I've been able to do something to maybe open the doors of opportunity to a few more people.
Yeah, I mean, it's a really generous thing. That's fantastic. I'll put information in the notes, but do you also want to describe how would people find this and take the course?
So I think if you look on, if you type Coursera and then Active Optical Devices, the course will come up and you should be able to find it. You can also type Coursera and then my name, and the course should come up. But these online courses it's really transformed education. I guess I would still say it's probably not as good as being in the classroom, but I think it is one way that we can share our knowledge with more people. And there are lots of examples of this. One example that I think maybe was a little before its time was the MIT Open Courseware project as well.
I remember that. Yep. Yeah, I mean, face-to-face interaction is always nice to have, but like you said, if not for something like this, people who just would never otherwise have a chance to get any exposure at all to the material now do have that exposure or that opportunity.
That's correct.
So, yeah, that's great. Okay, so Coursera, search on Active Optical Devices or search on Juliet Gopinath, and I'll put information in the podcast notes as well.
Thank you.
Yeah, well, thank you for spending the time. I know we took a while, but I appreciate your taking time out of your busy day and time away from your 6 different research projects in addition to your teaching and just life in general. So I really appreciate it. That was the 9th and final part of my conversation with Juliet Gopinath. Juliet also teaches a free online course on active optical devices. Just go to Coursera.org and search on Active Optical Devices or search on Juliet Gopinath. Subscribe to this podcast, and we'd really appreciate you helping to get the word out. Share this with friends and colleagues that come to mind when you think of network technology and optics. And leave a review on Apple Podcasts. We're also on all the other major podcast platforms. You may see the Cisco Podcast Network come up when you search for Cisco Optics Podcast. That's where we live, and you can find other great podcasts there too. Also, check out the Cisco Optics blogs at blogs.cisco.com and search on hashtag Cisco Optics blog, no spaces and no hyphens. We also have educational videos on YouTube. Just go to youtube.com and search on Cisco Optics. Thank you for listening. This is Pat Chow, Product Manager at Cisco Optics. Next time, we'll start a new conversation with a new guest. Until next time.